Okay, so I'm now streaming. And now recording. I'll just give it another minute or two and then start the lecture. Okay. So I guess I'll get started. Welcome back, everyone, to the fourth course, or fourth class of the course. So we were in the process of studying the global structure of large random trees. And so my plan for today is to finish with the description of the finite dimensional distributions of sampled points in large random trees, and then move on to start to extend that picture from the setting of trees to graphs which may contain cycles. So I'll remind you the theorem we stated at the end of last class, but just before I get there, I want to first refresh you or be a little bit more precise on my definition of binary leaf labeled trees, because those come up in the theorem. So these are trees where, leaf labeled trees where the root has one child and then all other non-leaf nodes have two children. And the leaves are labeled contiguously with, integers 1 up to k, where k is the number of leaves. So, for example, we could have a tree like this. One, two, four, whoops. 3, this would be an example of a binary leaf labeled tree. And we said that the number of binary leaf labeled trees with k leaves is 2k minus 2 factorial over k minus 1 factorial 2 to the k minus 1. All right. And so I'd also like to leave you with an exercise related to this. So I stated this formula as an exercise. I'd like to sort of slightly extend that exercise by describing Rémi's algorithm to you. So this is a way of constructing uniform leaf-labeled binary trees. So starting from, there's only one leaf-labeled binary tree with one leaf. So that's just this tree. Then we'll generate a sequence of such trees as follows. So for k at least 1, we build bk plus 1 from bk by doing this. So we choose uniformly random edge of bk. Subdivide the edge to create a new vertex. And then attach leaf a leaf labeled k+1. To the new vertex. Right, so in this example, if this were the tree, this would be the tree B4, and then to create B5, we would take one of these edges uniformly at random, so perhaps this edge here, break it in two so that there's two edges, and now in order to complete this to a binary tree, attach a new leaf with label 5, and that gives us the tree B5. Okay. So that's a pretty straightforward procedure. Notice, the edge next to the root can be subdivided. So this is sort of when I insisted last class on the fact that the root has exactly one child, and this is sort of important for this procedure, that the new leaf could be right next to the root. So now the exercise here is that that BK is a uniformly random leaf labeled binary tree with k leaves. And that's true for all k at least one. Okay, is that exercise clear? Good. So now having explained that, I hope that what I mean by leaf labeled binary trees is clear. And I'll remind you of the theorem we saw at the end of last class. So this said that if we look at the subtree of Tn spanned by the root and the k smallest labeled leaves, and then we reduce it to its shape, and then we record the vector of edge lengths along with that shape, then that converges in distribution after rescaling the edge lengths. I see I've made the same typo as last time. After rescaling edge lengths by n to the minus a half to a random binary leaf labeled tree with edge lengths whose density is given by this expression. So this expression in particular is symmetric in all of these edge lengths, which means that the limiting random tree has exchangeable edge lengths, and moreover, those edge lengths are so their joint distribution is independent of the tree T, and since the expression of this density only depends on the tree through insisting that it's binary leaf labeled tree with k leaves, that tells us that the shape is uniform over such trees as well. Okay, and then you can sort of, by doing a little bit of work with this density, you can extract the fact that that's sort of equivalent to saying that that the total length is gamma k half distributed, and if you divide through by the total length, then the proportion of that length falling on each edge looks like a Dirichlet random vector. Okay. So that's that escalated quickly. Someone wrote in the chat. Yeah. So I know there's a fair bit of content on this slide. I want to unpack it a little bit for you, and then that's the last thing I'll do on this section. In fact, before moving on to graphs with cycles, I think to get to really internalize this this message, you need to do some of the exercises that I wrote that relate to this theorem to sort of understand how the pieces fit together. But let me sort of sketch the key step of the proof of the theorem for you. Okay, so the key step is as follows. Okay, so we want to think about, I'll just scroll back to a picture I drew last time, which is, we already understood the lengths of these various branches and the connection with the Poisson process. Okay, but if we want to understand the shape of this tree along with the edge lengths, then we need not just to understand the lengths of the branches as they come along, but how they attach on to the to the tree, right? How these attachment locations behave. Okay, and so that's really the key missing ingredient in order to understanding the whole distributional convergence in that sort of somewhat wordy theorem. So if we write JNI for the index of the attachment point of the ith branch, remember, so this was the branch leading to the ith smallest leaf, so to Li. Okay. Then remember we already had a convergence, so I'm gonna which I'm now gonna extend. So jointly with the distributional result. So we had n to the minus a half tn1 up to tnk converges in distribution to the ranked sequence of atoms of this Poisson process. Then we also have that n to the minus a half jn1 up to jnk converges in distribution to a vector. So p naught u1, p1 u2, up to p k minus 1 uk, okay, where so u1 up to uk are independent and uniform. And this is true, so independent of each other, and also of the vector p1 up to pk. Okay, and I guess I should say here I'm setting p naught equals 0. Okay, so so what's this really saying? Let's look back at a proof from earlier to get a flavor for this. So we had this this combinatorial result about the joint distribution of these edge lengths, right? And the way that we proved this lemma was by saying in order to see these particular branch lengths, a certain thing had to happen. We had to have disjoint, sort of under the bijection, we had to see distinct values at various times. And then we had to see these other values being repeats, because that's what told us that we were joining to a previously discovered vertex and starting to grow a new branch of the tree. Okay, well, if I tell you that this value is one of, that this uniformly random integer happens to fall in this set, then it's just a uniformly random member of this set, right? And if this random integer happens to fall in this set, then it's a uniformly random member of that set. Okay, and in particular, its index among these previous entries is uniformly random. So that's saying when we see the repeat, when we see a repeat, it's equally likely to be a repeat of any of the previous values. Okay, so it's just uniform over those previous values, so its index is uniform. That's all that this statement I'm making is saying. That is to say, if we've already built, this much tree, and now the next, I tell you that the next value we see, we've been going along building the tree from, we'd happen to see the values 1 through 14 so far, and the next value, could continue extending this branch, but I tell you, no, it doesn't extend that branch. It's one of the pre-existing values. Then its location, the location where the new branch is going to start growing, is just going to be uniform over all of the previous lengths that we've already seen. Okay, so it could be here or here or whatever. Okay, so that's the sort of key point. It says that when we start growing a new branch, it's going to grow off of a uniformly random point. And so you can sort of imagine that saying something like, we take one of the existing lengths at random. Well, I guess there's a length and there's the length. We pick one of the existing lengths at random and split it and start growing a new leaf. So that maybe brings to mind a little bit Rémi's algorithm that I described. Okay. Right. So after all that back and forth, so this fact that jointly with the convergence of the lengths of the points of the Poisson process, the attachment locations just look like sort of uniform on the previously grown tree. This is just because if we condition on tnk minus 1, then the attachment location. Oh, that was bad. Of the branch leading to Li, to Lk is uniform on Tn k minus 1. There's a nice question from Lior in the chat that I'm going to postpone the answer to because I sort of have something prepared and it'll make a little more sense after I say just a bit more. Okay. So once now you have a joint distributional convergence of the lengths and of the attachment locations. Okay. And once you've established that, then now we can sort of describe the full limiting process that we would, if we want to understand the tree with edge lengths sitting in the limit here, we can just describe the limiting construction that corresponds to the finite construction. We understand asymptotically how the finite construction is behaving, and now we say, well, what does that mean in the limit? And then, what I'll do is just describe that and assert that it leads to a tree with this density. And proving that is sort of a fairly straightforward exercise in calculus and probability. And I'll leave it as an exercise. Even though the result is sort of beautiful and maybe hard to guess in advance, once you know it, the proof isn't too bad. So given this asymptotic, distributional asymptotic information, the proof boils down to the following statement, I guess. So let's build a sequence of trees right in the limit. We're going to build a sequence of binary leaf-labeled trees with edge lengths in the limit. So we'll start from a tree T naught, which is just a single point. And then, so for k at least 1, we'll let tk, so this is going to be let me use that acronym I introduced, BLT, binary leaf labeled tree with edge lengths. Which is formed from tk minus 1 by attaching a line segment of length pk minus 1. So these are the points, the atoms of our Poisson process to a uniform point of tk minus 1. and giving the new leaf label k. Right. So then you can notice if I do that. So what's the construction here, right? It's let me grab my Poisson process. Right, so our first tree looks like this branch here. This is T1. And then our second branch has length. So I should really add a leaf at the end here with label 1. And then our second branch is leaf, has sort of this length here and a leaf with label 2 at the end. And this attachment point was just uniform along the length that I'd previously constructed. Okay, and then the third branch has this length and attaches to a uniformly random point. Maybe it attaches here, it has 3 at the end, and so on. Okay, so you see in particular that so this is the tree T3, and I always have that, that the total length of TK is just PK. Right, because I'm just adding the difference needed to get me to the next atom at each step. So this is a tree. This is a tree here which has 5 edges, right? 1, 2, 3, 4, 5. So when we do this attachment to a uniform point, we're always subdividing an edge, and so that creates 2 edges out of 1, and then we add an additional new edge to the new leaf. Okay. So then in this construction, the tree with edge lengths that we end up with has density pk e to the minus, well, so maybe I should write it as the sum of the lengths times e to the minus the sum of the lengths squared on 2. Okay, so this is precisely the thing that that shows up in the statement of the theorem, right? And so the idea is essentially once you have all this data about how the construction in the finite setting converging to the construction in the limiting setting, then that also means that if you can describe the distribution of the joint distribution of TK and the lengths in the limiting setting, you also get convergence to that limit object. Okay, so now I'd like to return to so yes, so Leor asked in the chat. So now uniform means with respect to the length function, and that's correct. So this is, if you like, if you continue to identify. So the question is, what's the meaning of uniform here? If you continue to think of the identification between the non-negative real line and the set of points of the tree T, there are these points which got identified, but there's just a bounded number of those. So if we think about Lebesgue measure on the interval P0 up to P3, then we're just choosing a Lebesgue distributed point on this interval here as the next attachment point, as the point where P4 will be attached. Okay, and one way to do that is you could say that so the attachment point of so pk plus 1 to the tree tk is just given by pk times a uniform random variable uk plus 1. So this is a uniform 0, 1 random variable independent of the other randomness in the construction. Okay, and that's precisely how I formulated things up here by selecting the attachment location using a uniform random variable. Okay, and so now there's this question of why this should be uniform, and so there's some nice distributional identities involved in that. But roughly speaking, if I tell you that, so if you believe this. If you believe this, that TK is uniform for a given, so let's think about it one step at a time. The first tree is just a branch to a leaf, okay? And then what happens is we attach another branch to a random point on the first branch, okay? And now it's not the case, if I show you this whole picture, it's not the case that the next attachment point is equally likely to be any of these three segments. This one is longer, so it's more likely to attract the next attachment. Okay, but if I don't tell you the lengths and I only tell you the shape, well, this theorem here tells you that the distribution of the lengths is exchangeable. I could permute the edge lengths and I would get another tree with the same distribution. Okay, so that means that if I hide this picture, if I cover this up and I only show you the combinatorial tree that you got from the construction so far, then now when I ask where does the next attachment fall, it's equally likely to fall in any of these three edges. Okay, and so that means that if I only look at the combinatorial structure, I will be just attaching to a uniformly random edge, which is like what Rémi's algorithm does. Okay, and then the beautiful bit of distributional magic that you have to check is that this exchangeability is maintained by the process. So after we pick a random edge, then probably we picked one of the longer edges. So that means that sort of, if I tell you that you picked this edge, then that breaks the symmetry between these three edges, because you're more likely to pick a point that's in a longer edge. But then you subdivide that edge, which makes the two pieces smaller again, and attach a new piece. And sort of magically what comes out of that is precisely, again, an exchangeable vector of random variables. So with this sort of the distribution corresponding to this density here. Okay, so there's this exchangeability that's maintained by the dynamics, which means that if you ignore the edge lengths, you actually precisely see Rémi's algorithm. Okay, so that's as much as I'm going to say about the line breaking construction. I'm just going to finish that chapter with a picture of the large n limit. So this is if you you can think of this as, it's in the finite world, but if you first take n to infinity, so you're doing this line breaking construction starting from the Poisson process, and then you take k to infinity, so you get a bushier and bushier tree, you end up with some sort of random fractal, which looks a bit like this. So this is called this is a simulation by, for those who haven't seen this sort of picture before, it definitely deserves to be shown at this point. So this is a simulation of the limit, which is called the Brownian continuum random tree. By Igor Korchemsky. I would look on, someone asks what software was used to produce that. I would look on Igor's website. I think it's Mathematica, yeah. So the density only sees the length of edges and doesn't really weight based off of the other information in the tree. Yeah, that was, I was just reading a question in the chat. That's exactly right. So the fact that the other information in the tree doesn't figure in the density means that if you integrate out over all the information except for the shape of the tree, you must just get a constant. And so that's what says that the tree itself has to be uniformly distributed over all the possible shapes. Right. Any other questions about this bit of the story? Okay. Good. So let me just, maybe this is a good moment for me to have a sip of water. Okay. So we'll move on to graphs with cycles now. And so we're going to be looking at graphs, as it says here, if you can read my cursive, with boundedly many cycles. Okay, so in the same way that the theorems we were proving last time involved fixing some number k, which could be 10 or 1,000, but didn't change with n, and then looking at the subtree spanned by the root and k leaves and letting n tend to infinity. Here we're going to be fixing, this is going to be another fixed parameter, as large as you like, but constant and not varying with n, the number of cycles. Okay, so that number needs its own name, and it's called the surplus of the graph. So if I give you a connected graph, G, with vertices V and edges E, then the surplus of G. So this is the number, so E of G minus V of G plus 1, okay, which is the number of edges more than a tree that G has. Okay, right, so a tree, right, a tree has one fewer edges than vertices, and so this this number here is 0 for a tree, and so we'll be interested in this section describing the asymptotic structure of large random graphs with fixed surplus. Okay, so let me, that we need, so this is another, just a uniformly random sample from a set of graphs. Before our set was labeled trees within vertices. In the current setting, we'll call the set GNS. So this is the set of so connected graphs whose vertex set again is the first n integers, and now whose surplus, so this is going to be my notation for the surplus of the graph, is equal to this fixed value s, and our aim is to understand the typical structure of a uniformly random sample from GNS. Okay, and note that So this generalizes the first, this setting sort of is an extension of the setting of the previous 3 lectures, because if we were sampled, if we take S equals 0, then that's just looking at connected graphs, which are trees. So that's the same as sampling a random tree from the class Tn. Okay, so this generalizes what we did for trees. Okay. Any questions about that? So we're going to have to work a little bit harder than for trees, but lots of the work we did for trees will pay off in the study of these graphs as well. But I'm not going to. I mean, the part where we use what we already know for trees will be fairly easy because we already know that stuff. And so, I'll just sort of start focusing on the core of the issue. The core of the challenge to go beyond trees, and the thing is actually called a core, which is the core of the challenge. So, so if we have a connected graph, then we want to understand the bit of it that's not tree-like. We'll call that a core. So this is a connected graph with minimum degree 2. Right? A fundamental property of trees is every tree has a leaf, or every tree has a vertex of degree 1. And so a core is unlike trees in that way. Okay, so that's what a core is. And now if we're given a connected graph, we can also talk about the core of a graph. So so given a connected graph G, the core of G, so this will be the maximal subgraph of G that has minimum degree at least 2. Yeah, so here I should say at least 2, sorry. Okay, and so I'll leave it as an exercise to show that, to say that, so for any connected G, there is a unique maximal subgraph of minimum degree 2. So that this, when we write the here, this really is we're getting a well-defined notion. And it's not that hard an exercise. I'll show you one way to find the core of a given graph, and you'll sort of see from the procedure that the core is indeed a sort of unique and well-defined object. Okay, so if we take this as our graph, I didn't want to draw a sort of complicated example. You can, if you're interested in finding the core starting from the graph, you say, well, we're not allowed to have any vertices of degree 1, so we may as well remove all the vertices of degree 1. The core, whatever the core of the graph is, it has to be contained in the graph we get by removing all the degree 1 vertices. Okay, and now having done so, some new degree 1 vertices might appear when we do that. So they also can't be in the core. And so we'd better remove them as well. Okay, and if you just sort of keep doing that until you can't do it anymore, either you eliminate your whole graph, in which case you started with a tree and the core is empty, or you end up with some non-trivial graph, and that graph is the core of G. Okay, so that's sort of one way to find the core, which also shows that the core is unique. And so we're going to study the structure of you know, a uniformly random graph in GNS by building up from the core. Okay, is the setting clear? Just smiling at the chat. Okay, so let me give you a sneak preview of where we're headed. Okay, so if I fix some non-negative integer s and let G be a uniformly random graph in GNS, then, so as n tends to infinity, if I look at the number of vertices in the core, I think I'm actually going to call the core C of G because that's what I do in my notes. And that's my notation for the core of G. Okay, so the number of vertices in the core again has order n to the half. And if we divide by n to the half, it converges in distribution to the square root of a gamma. The gamma now has parameters 3s minus 2 over 2.5. Okay, so this is a random variable with density. So x to the 3s minus 3 over 2, e to the minus x squared on 2 on 2 to the 3s. My s's look a bit too much like 5s, sorry. Minus 4 on 2, gamma of 3s minus 2 on 2 on for non-negative x. Okay, so we already saw square root gammas show up when we were studying the total length of T and K just a minute ago. All right, so that's sort of suggestive. And so that's the first part. We can understand the total length of the core. We'll also need to understand the shape of the core. I won't give you a sneak preview of that. It's coming pretty soon. But also, if we want to build up from the core to the whole graph, then there is indeed limiting line breaking construction of this uniform graph. So starting from the core, and which generalizes that of which we saw for the trees. Okay, so continuing with the sneak preview, you know, in the limit, what you're going to see is the core is going to converge to some random shape, which is like a graph with minimum degree 2 and with edge length. And then there will be a stick breaking construction or a line breaking construction starting from this picture. So that will look something like, you know, taking the atoms of some Poisson process to make branches and then attaching those branches at uniform locations on the core or potentially on the previous branches. Okay, so that's very much analogous to the story we've told already. And again, there's enough sort of nice distributional properties here that you get nice exchangeability of the edge lengths and various kinds of uniformities in the construction. Okay, so that's the picture of what's going on. The nice question. There's a couple nice questions in the chat. Yinon asked, are the graphs in GNS rooted? So I haven't taken them to be rooted. One thing you can do is root, for example, if they could be taken to be rooted. And in fact, when the surplus is exactly 1, it's sort of nice to take them to be rooted objects. But if you do, so if let me talk about that just briefly. There's another version of the whole story I told, and I had to make a choice when I wrote the notes about whether to take these as rooted or unrooted objects. I chose unrooted because this core construction is, I think, most natural the way I described it. But there's another option, which is to choose a canonical label like vertex 1, for example, and then say that vertex 1 and the path from vertex 1 to the core just count as part of the core. So you've actually rooted the whole core, and so 1 does not count as a leaf anymore. It's a root. Like in our rooted trees, the root, even if the root has degree 1, it doesn't count as a leaf. Okay, and so you fixed a root, and then you only do the core constructions. So then the initial picture looks like this. Okay, this would be the rooted core. Okay, and you could tell the whole story for rooted cores instead of unrooted cores. It's a little bit, I mean, that feels a little bit more artificial, which is why I didn't do it. But then, then in this picture, the thing you start with would not look like this. It would look like, that or something. Okay, and you'd go from there. The distributional identities work out in either case. And in fact, there's an advantage to using rooted cores, which is that in the case that the surplus is exactly 1, the core just sort of forms a loop, and there's sort of not enough structure in the core for things to work out exactly the way one would like them to. Well, more concretely, in order to have this sort of line breaking construction, in the case where S is 1 and the core is just a loop, you actually need a root. You need to take the rooted perspective in order for all the nice distributional identities to work out. Okay, so I sort of gloss that a little bit or outsource it to the notes, because the combinatorics of this case aren't very hard. It's just when you do things in the unrooted way, it acts as a special case, and so I shunted that to the side. But yeah, so you put your finger on a very nice question. There was some question about whether the core is connected. It is always connected, and it's a nice question of why. But one way to think of it is sketched by Serta in the chat. Another way is just to say visually, if the core has 2 cycles, well, since the original graph is connected, there must be a path between them in the graph. And now this is, if you take any such path between them, this gives you a graph with minimum degree 2, and so that must be part of the core. Okay, so that's one way to show, to sort of see that the core should be connected. Okay. So let's next just briefly think about the combinatorics of, so this construction of the core from G is unique, right? There's only one way to do that. But you can ask, if I show you, I tried to cover up the graph on the left just by putting my hand over my iPad. That doesn't really work for you. If I hide this graph and ask how many pre-images were there here, there's some calculation to do. This isn't a bijective map, right? There's lots of potential ways to reconstruct those dangling trees. But these are all trees, and so now our combinatorics of trees can help us out. Okay, so let's use that. So I'm going to take this picture and recycle it for the next observation. Okay, so here's the observation. Okay, so if you give me any core C whose vertex set is contained in N, and let's write k for the number of vertices in that core, okay, then the number of graphs G such that so the vertex set is the integers 1 up to n, and the core is C, is just k times n to the n minus k minus 1. Okay. So what so that's saying that going back this way is a there's k times n to the n minus k minus 1 preimages where k is this. So here, k is 8 and n is 14 or 15. Okay, and the reason for this is quite straightforward, right? If we look at this graph on the left, and allow me to just delete all of the edges of the core, okay, but none of the other edges. Okay, well, that just gives me a forest, right? All of those bits that got removed to form the core are a forest. And if I view the vertices of the core as the roots in the forest, right, then this is just some arbitrary forest of rooted trees whose roots are given by the labels in the core. Okay, so, and we know how to count forests, we did it before. So that's where the formula comes from. So just to, at least write down some sort of words which correspond with that picture, even if I'm not being sort of 100% formal. So the operation of removing the edges of the core, so that gives a bijection between this set and the set. We had a name for this, Fn, right? Remember that we wrote Fn with a superscript for forests with vertex set n, whose root set was given by the superscript. So here the superscript is Vc. And this set has size k times n to the n minus k minus 1. We proved that using our bijection. Okay. So that's that's a quite easy bit of the combinatorics, knowing how many ways there are to reconstruct the graph from its core. Okay. But if we want to know how big a typical core is, we need to know a bit more, right? Because if the number of ways to build the core itself is very constrained and there's lots of ways to build the trees, then a typical sample will have lots of vertices in the trees and quite a small core. Whereas if there's tons and tons of ways to build the core, that many more than the ways to build the forest, then we'd expect to see lots of vertices in the core and relatively few vertices in the forest. Okay, so there's that sort of combinatorially, we're interested, in order to figure out what a typical sample is going to look like, we need to sort of know what our options are. So really what we're heading towards is counting or approximating the size of this set in order to understand the typical structure of an element, just like we did with trees. Okay, but we're doing that by building up in stages, sort of first by understanding the number of possibilities for the core, and then we'll combine that with this information about how many ways there are to go from the core back to the full graph. Okay. Right. So so the point is that if I give you, these two pictures, so someone asked in the chat, how do you go back in the bijection there? The point is, if I show you the core and I show you this picture of all of the trees of this forest, then you can recover the graph G just by gluing the trees of the forest onto the corresponding vertices of the core. So this one goes on here, and this one goes on here, and this one goes on here. and so on. Okay, so that's the procedure. Right. Okay. So so we want to simplify our lives even a little bit more, and so the next step really corresponds to when we just did a thing which was passing from a tree to its shape, right? And we did that by essentially taking all of the degree 2, all of the paths of degree 2 vertices, or in the tree setting, vertices with only one child, and replacing all those by single edges and just recording their lengths, right? So we're going to do a similar thing here. We're going to take this picture and collapse it down to a picture where these degree 2 paths get suppressed. Okay, so so let me, and that gives us a thing called the kernel. Okay, so so given a graph G, the kernel K of G. So this time we're going to get a multigraph. So this is obtained from the core. By replacing, so maximal degree 2 paths by edges. Okay, so I might have saved a, no, but okay, so we have, I'll start again from here. Right, so with this graph, we made this kernel, this core, and then from there, we're going to so turn this path into an edge and this path into an edge. And so we'll end up with a kernel, which is just this graph. Okay, so it's a multi-graph in general. Here we end up with a graph with 2 vertices and 3 edges connecting them. Okay, and actually already in my drawing up top, you saw another sort of thing that can happen, which is that you can end up with loops, right? So if in this example there had been, say, an edge between 12 and 15 here, then the core would have had would have included this loop 5, 12, 15, and then we would have ended up with a more complicated kernel here, which would have had a loop hanging off of this edge. Okay. So both multiple edges and loops can arise, and whoops. And now we'd like to understand, once again, we have a construction which is, unambiguous in one direction. So going from the graph to its core is there's only one way to do that. And there's only one way to go from the core to the kernel, right? And we said we understand how many ways there are to go from the core back to the graph, but how about the number of ways to go from the kernel to the core? Okay, and that's a little bit, well, it takes a moment of thought, and it's what we'll go to next. I'm just looking at the chat and seeing a question. Does the cycle kernel have no vertex? That's correct. So in the drawing that I just did, so you end up with a graph whose well, with a multigraph with the following structure. So once we'd added this edge here between 12 and 15, we ended up with a loop. So this is an edge connecting 5 to itself. I mean, if you like it, its only vertex is 5. But that's one question you might have been asking. Another question you might have been asking is, what if our original graph, for example, only had didn't have this internal path and only had these dangling trees over here, right? So in that case, the kernel would not have this path. Okay, it would just be a cycle, or the core would just be a cycle. And then there's a question of how do you want to define the kernel? I mean, if you when you suppress all of the edges on this, the vertices on this path, do you just end up with nothing, or do you end up with like an edge that has no vertex? Okay, so is this like a graph with one edge and zero vertices? You have to make some choice for what you mean by that. But it's just a convention in either way. And mostly I'm actually going to sort of studiously ignore this case of surplus one, just turn my head away and pretend it doesn't exist, because the combinatorics, it's sort of it's its own special case, but the combinatorics is no harder. It really follows the same pattern. And so I don't feel like a lot is gained by dwelling on it. I sort of leave it to you to extend the computations I'll show to that case. Okay. Good. So let's think about, here's an example, which I'll grab. Let's think about if I show you this kernel. So up at the top, right? It's a multi-graph, could be the kernel of some graph. And I want to say, how could we, what data do we need to reconstruct this kernel, which let's say it's the kernel of the core I drew down below. Right. What data do we need to go from the picture on the top to the picture on the bottom? Okay, so we'll fix a core C and let K be the kernel of C. Okay, then to reconstruct C from K, well, first I want to list the edges of, so I need to tell you what basically what appeared on the various paths of the kernel, right? That's what we need to know to go from the kernel back to the core. What were those paths that got contracted? Okay. So you list the edges of K as E1 up to M. M is just the total number of edges. So and we want everything to be as canonical as possible. So let's say in lexicographic order. So that means that we prefer edges with smaller vertices. So in this example, we might pick this edge. So that would mean this is E1. Both of its endpoints are 1. This would be E2. And then here we have 3 copies of the same edge, E3, E4, E5, E6, and finally E7. Okay. And now we'll list the paths I realized in the course of this lecture that I'm using the letter P for too many things. I think they were paths in the tree, and then they were points to the Poisson process. Now they're going to be paths in the core, but I apologize. There's no Poisson process anymore, so you shouldn't be distracted or confused by that. So we'll list the paths of C corresponding to the edges of K in that order as P1 up to PM. Okay, so in this example, so P1 is this path here, 5, 6, 7. Okay, but there's a little warning already when I do that, because I could have written it as 7, 6, 5, and it wouldn't change. Either way, I'm going to get the vertices 5, 6, 7 in order attached around a loop to vertex 1, right? So there's a little bit of ambiguity I'd better keep track of. anyway, P2 is just the vertex 8. That's what happens on that edge. P3 is the path 9, 10. Okay. P4 is, there's no need for a path because the edge doesn't get subdivided in the core. It's just empty. It's empty path. P5 is just the vertex 11. P6 is 12, 13. And P7 is 14, 15, 16. And again, there's a warning because I could have listed that, because this is a loop, I could have listed that in the reverse order and it would have corresponded to the same reconstruction. So, or 16, 15, 14. Okay. So you see, if I tell you the paths, you can reconstruct the graph from the kernel, but that reconstruction isn't unambiguous. There's some symmetry factor of 2 for each loop, but there's another symmetry factor as well, right? Because if these three, remember these 3 edges, 3, 4, and 5, all join the same 2 vertices. So if I list those paths in a different order, I still get the same graph. It's the same labeled graph. It has the same vertex set and the same edge set, right? So these could have been these could have been in any order. Okay, so that's a symmetry which needs to be accounted for. There's a couple of so there's the symmetries to be accounted for. There's also the question of, you know, if I show you the kernel and I'm asking about how many ways there are to reconstruct some core, well, this time I showed you the core and we worked out what the reconstruction was. But if you didn't have this picture, okay, and you were just asking what sorts of sets of paths are allowed, well, there are some constraints, right? One is that for a loop edge, I'd better have at least 2 vertices on the path, right? Because if the path I wrote if for P1 here, I'd just written 5, then that would correspond to a reconstruction, which was this, which had a 5 on this edge, but that creates 2 edges between 1 and 5. And our original graph didn't have multiple edges and loops. So you're not allowed to just have a path of length 1 on a loop, okay? So that's one kind of constraint. Another kind of constraint is that what if, I couldn't have had both P4 and P5 being empty, because that would have corresponded to leaving E4 and E5 both as single edges joining vertices 2 and 3. And that's a multiple edge in the original graph. Okay, and there are no multiple edges. We started from a simple graph. Okay, so when I see, so what are the constraints I just described? The constraints are so the loop paths have at least 2 edges, at least 2 vertices. And there's at most 1 empty path per edge, per kernel edge. Let me say per kernel multi-edge. Okay. So those are the restrictions on what sorts of paths will legitimately yield a reconstruction of a core for a kernel. So let me just give a definition corresponding to that. So if I'm given a kernel K with edges E1 up to EM, we'll say that sequence P1 up to PM of vertex disjoint paths is valid if the first thing is that whenever EI is a loop, then PI has at least 2 vertices. And the second is that whenever, so we have some set EI1 up to EIJ, which are all copies of the same edge, then at most one of PI1 up to PIJ is empty. Okay, and so now so a kernel K plus valid paths P1 up to PM uniquely specifies a core. Okay, but we have to account for these symmetry factors. So if edge E of K has multiplicity J, then permuting the, so then there are J factorial permutations of the paths corresponding to copies of E, which leave the reconstruction unchanged. And likewise, if EI is a loop, then reversing PI leaves the reconstruction unchanged. So here we have a symmetry factor J factorial, and here we have a symmetry factor of 2. There's a question in the chat. When EI is a loop, it may also have 0 vertices, may it not? I think you drew one such kernel buff, but I may be mistaken. Yeah, so the kernel can have loops, but those loops must have had vertices on them in the graphs that the kernel came from, because the original graph didn't have loop edges or multiple edges. Okay. So now we have a reconstruct. This is enough. Basically enough combinatorics now. So that's the sort of care we need to take in order to figure out how to reconstruct cores from kernels and what the symmetry factors are. And so this tells us that if you fix a given vertex set V, then the number of cores with the property that the vertex set is V and the kernel of C is some particular kernel K. That's just so the number of sequences of valid paths with combined vertex set V, so the remaining vertices. So we have to use the vertices of V which do not appear in K to build those paths. and then we have to add in our symmetry factor. So the symmetry factor had two parts. Each time we saw a loop, we had to count a half. So that means for each, so we have 2 to the minus multiplicity of e for each loop. And then each time we saw an edge that had multiplicity j, we got a factor j factorial. So we have multiplicity of e factorial on the bottom. Okay, so so that's what do I mean by multiplicity? So it's exactly what it sounds like. So this edge here has multiplicity 3, right? So the multiplicity of the edge 2, 3 here is 3 because there are 3 copies of it in the kernel. Okay. So this is an exact formula. You know, you can reconstruct the core from the paths. So here m is the number of edges. Okay, you can reconstruct the core from the paths uniquely as long as they're valid, but there are certain permutations of the paths which yield the same core. So maybe the use of my word uniquely is confusing there. I mean that once I tell you the paths, there's no ambiguity about what core they reconstruct. But there are different sets of paths which reconstruct the same core, and that's what this symmetry factor here is accounting for. Okay, so what the numerator is doing is saying if you have an edge of the form, you know, like 4, 4, it's a loop edge, right? Then you're supposed to count. Then you need to divide the number of possible reconstructions by 2, because we saw that listing the path or listing its reverse yield the same reconstruction. Okay. Yeah, thanks. So I could put the indicator should really be in the exponent so that the whole thing doesn't become 0. Okay, so this way, if e is not a loop, the numerator just becomes 1, and if e is a loop, then it gives us a factor of a half for each copy of that loops, right? So there could be multiple loops sitting at the same vertex, and then each of those, the corresponding path, could be listed in either direction. Okay. And then so you know, a bouquet of loops like this would maybe with 3 loops would give us you know, a 2 to the minus 3 factor, and then edge, you know, 5, 7 with multiplicity 5 would give us a 2 to the minus 5, would give us a 5 factorial factor, because any permutation of those edges and edge paths yields the same reconstruction. Okay, so that's the second. That's how. That's a formula for how many ways there are to go back in this diagram. You know, here we had this k times n to the n minus k minus 1, and now we have some more complicated expression. But it's basically like the number of valid tuples p1 up to pm, so sequences of paths, 1 for each edge, and then so we have that, and then times some symmetry factor, which I'm going to call sigma of k, which depends on the kernel. Okay, so that's actually a definition. So I'm going to call this quantity here sigma of k. Okay, and so the last thing I'd like to do for today is to extract some asymptotics from this formula. So here's the proposition. Let's fix a kernel K with vertex set, say the first K integers and with M edges. Okay. And as, so I'm going to look at cores with vertex set 1 up to L, where L is large, and ask how many there are that have this kernel. So the number of cores C with, so vertex set L, and with kernel K is, so 1 plus little o 1 times L minus K factorial L to the M minus 1 over M minus 1 factorial times sigma K. Okay. So you can think of this. Oh, I see there's a question in the chat. Maybe this is a good time to answer it, because the next thing I'm going to do is start to talk about the proof of this. For the denominator, this should be once per multiplicity set and not for every edge. Yes, and that's also true for the numerator, right? So in this product, I'm doing it once per multiplicity set. So if the edge, you know, if in that picture I drew, 5, 7 showed up with multiplicity 5, and so that gave us a 1 over 5 factorial. It didn't give us a 1 over 5 factorial 5 times. And here, this edge 4, 4 shows up 3 times. That gives us a 2 to the minus 3, but only once, not 3 times in the product. Right. Okay. So let's just think about what this term here means, right? So this looks like we're ordering a set of size L minus K. Okay, well, if you think of, yeah, so ordering a set of size L minus K, and then if you think of this L to the M minus 1 as a L minus K to the M minus 1, then you can, which is equivalent when L is large and K is fixed, right? Then this looks like choosing M minus 1 locations to split up that ordered list. Okay, so so the numerator looks like order the vertices of C, which are not vertices of K, split them at M minus 1 locations to form M pieces, okay? And then assign those pieces to the various edges of the kernel. Okay, except that you know, once I have the pieces, if I permute the pieces and sort of permute the assignment as well, then there's some symmetry factor from that, and that corresponds to this M minus 1 factorial here. Okay, so so this is really saying that up to this symmetry factor sigma K, the number of ways of reconstructing the kernel from the core from the kernel just looks like the number of ways of ordering up, building one big path and then cutting it into the M parts that I need to. Okay. So I think that maybe I'll just say that in very slightly more detail, and then we'll call it a day. Right. So so to reconstruct C from K, we can first order the vertices of C minus the vertices of K as S1 up to S L minus k, and there's L minus k factorial ways of doing that. And then we can, so choose, so some spots to split this ordered list into paths. So I'll call those I0 less than I1, less than I2. The pieces, remember, so I'm trying to split this into m paths, but those paths can be empty, right? In our reconstruction, we did allow for the possibility of empty paths. So im minus 1 most im. So we'll start at 1 and end at L minus k plus 1. And there's, so L minus k plus 1 to the m minus 1 over m minus 1 factorial ways of doing this. Okay, so what am I doing here? I'm choosing m minus 1 values between 1 and L minus k plus 1, and then ordering them, right? So the numerator is choosing the values, and the denominator is accounting for the symmetry of the ordering. And that's just 1 plus little o1 times L to the m minus 1 over m minus 1 factorial. Okay, and then the last step is so we'll let P1 be the path that goes from I0 up to I1 minus 1, and then P2 be the path that goes from I1 up to I2 minus 1, and so on, right? So Pj is the path that goes from Ij minus 1 up to Ij minus 1, and the last path goes from Im minus 1 all the way to Im minus 1, which is L minus k. So the last path ends at the last vertex. Okay, and then so then the question is just, if we do this, sometimes we might not have written down a valid set of paths, right? The number we just wrote here, L minus k factorial, L to the m minus 1 over m minus 1 factorial, is the thing that we're claiming up to the symmetry factor is the number of reconstructions. Okay, and so we know where the symmetry factor comes from. The other thing to say is just that is it the case that up to 1 plus little o of 1 error, we always get a valid reconstruction here? Well, what were the constraints? The constraints were that the path was always that we didn't have multiple empty paths along a multiple edge, and that any loop had at least 2 vertices on it, right? But when L is large and K is bounded, and we're splitting a very long path L into a bounded number of pieces, typically those pieces will all have length of order L. Okay, so there'll be these. So if we pick these values randomly, the probability that 2 of them are the same or are adjacent to one another is very small. Okay, so the probability that the reconstruction is invalid is asymptotically very small. Okay, so just let me say if Ij, to make that a little bit more formal, if Ij minus 1 is bigger than Ij minus 1 for all j from 1 to m, then P1 up to Pm are, so this is one way, I'm just saying one way for the reconstruction to be valid, but it happens most of the time. So then these all have at least 2 vertices. So this vector is valid. Okay, and so choices of I1 up to Im minus 1 with this property that the gap between Ij minus 1 and Ij is at least 2 for all j dominate the total number of possibilities. Okay, so it follows that the number of valid P1 up to PM is just 1 plus little o of 1 times the product of these terms up here. So. Okay, so that's the last thing I wanted to do today. We now have an asymptotic formula for the number of cores corresponding to a given kernel. That's now a simpler. It's not exact. It has this 1 plus little o 1 term, but it's good enough for probabilistic purposes. In our reconstruction up here, right, where I wrote more complicated expression, we can now say, well, it's more complicated, but it's basically this. Okay, and now, so that gives us enough detailed combinatorial data that next class we can finish the probability and describe the sort of global limit of a large random graph with a bounded surplus. Right. I see a private chat correcting me on one point, so I'll have to think about that offline. Maybe there's a some error in my computation. Yeah, I think that the point is correct. So there's because these sequences, because I've only taken I1 up to IM minus 1 weakly increasing rather than strictly increasing, the symmetry factor on the bottom isn't always m minus 1 factorial. So if they're equal, then there aren't actually, if I2 and I3 are equal, then permuting them doesn't change the ordering. So there's slight imprecision. This isn't exactly the number of ways of making the choice, though. Once I pass to an asymptotic, this formula is still valid. But if I want to be perfectly accurate, then I need to account for, I need to count slightly differently here, depending on whether or not there are repetitions among the I1, I2, and so on. Okay, so thank you for that, private chatter. I think I'll call it there. I'm happy to stick around and answer some questions, but I'll stop recording and stop the stream.